I'll be working through section 411, linear programming. I'll be working straight from the book. You're going to need to have the book handy and probably reference as we go, because it's a longer process to find the solutions, and I would like you to be able to reference the book and reference the video and maybe go over this example multiple times to make sure that you understand what we're doing. Okay, I'm going to read the example. A school board is investigating various ways. I'm on page 157, by the way. The school board is investigating various ways of composing the faculty for a proposed new elementary school. They can hire teachers and aides. The amount of money the school district will have to spend on salaries each year depends on how many teachers and how many aides are hired. Now here they list the different variables. T will be the number of teachers, A will be the number of aides, D will be the number of thousands of dollars spent annually on faculty salaries. The board finds that the average teacher's salary is $15,000 and the average aide's annual salary is $10,000. Since there are T teachers and A aides, so they're going to say that the money they spend on salaries, which is represented by D, is the dollars, is $15,000 for each teacher and $10,000 for each aide. That makes sense. So D is the function of two independent variables, T and A. This means that, we talked about this before, independent and dependent variables. The money spent not only depends on the number of teachers hired, but also on the number of aides hired. You don't look at the money spent and then work your way backwards. The money you spend depends on, if you hire 2 teachers and 1 aide, you would spend $40,000. You have to put those two numbers here to get your independent or your dependent variable out. The money spent depends on how many people you hire. So we want to look, first of all, we want to talk about domain. Domain is what our independent variables could be. In this situation, then how many teachers could you hire? Well, you could hire no teachers, right? So T, we could hire no teachers, or we could hire an infinite number of teachers. That makes sense. But could we hire -4 teachers? That doesn't make sense. So we can't hire negative numbers of teachers, just like we can't hire negative numbers of aides. And so right away, our domain is restricted just by reality. Reality is you cannot hire a negative number of teachers. You cannot hire a negative number of aides. So now, as they're doing their research, the school board finds that, so right away we have another thing, that T has to be greater than or equal to 0, and A has to be greater than or equal to 0. Those are another 2 set of criteria that we have to have for our answer. Next, they find these requirements that the building can accommodate no more than 50 faculty members total. So, and what represents the faculty? Well, the teachers plus the aides cannot be greater than, they have to be less than or equal to 50, period. So if you have more than 50, it won't work. So this is another restriction. We start writing down these restrictions and these specifications in math language so we can solve it like a math problem. A minimum of 20 faculty members is needed to staff the school. That means you have to have at least 20, so T plus A has to be greater than or equal to 20. The school cannot be run entirely by aides, so there must be at least 12 teachers. So teachers, T has to be greater than or equal to 12. And for a proper teacher to aide ratio, the number of teachers must be at least half the number of aides. So here the teachers have to be greater than or equal to 1/2 the number of aides. And it is impossible, obviously, to hire a negative number of teachers, which I already noted here. You can't have negative numbers. All right, so now the tendency will be go straight after this equation. We don't really want to do that. That equation has 3 things that we don't know. That makes it hard to solve. These have 2 things that we don't know: teachers and aides. And that's what we start focusing on. We have to find a minimum cost. But in order to find a minimum cost, we have to see what set of answers that we would have once we graph all these things. So to graph them, first T, if I'm going to put them on an XY axis like this, like A, let's see, what do? They put aides on the Y axis and T on the horizontal axis. If A has to be greater than 0, we've got to do everything over here. T is greater than 0, everything over here. So rather than graph all 3 quadrants, I'm only going to graph the first quadrant. There's no need to graph these other 3 quadrants. They don't have answers in them. They're already restricted. Because the number of aides can't be negative, and the number of teachers can't be negative. So I've taken care of this by just drawing that part of the graph. Now, in this situation now, I know that my t is more like my x's, so I can actually think of it this way. I can think of this as x is greater than or equal to 12, right? Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, that's going to be bad. We're not going to be able to fit all our equations on if we do that. So let's do this. Because I know the scale that we're going to have to hit with this, we're going to have to be careful to make sure we draw it a scale. So we're going to need to be able to go up to 50 on both of these axes. 20, 30, 40, 50, 10, 20, 30, 40, 50. All right, so this is going to be 50, this will be 50. And here what do we have? We have that x is going to be greater than or equal to 12. 12 will be right here, which means my first line that I'm going to make actually is a solid line. This line represents this equation here. I've got to be greater than or equal to 12, which means everything over here. There's that one. How pretty. Now, if this really were x's and y's, and I had t plus a, or x plus y has to be greater than or equal to 20, it's easier to graph this. I'm doing this one right here. If I go ahead and put it like we normally have it, y is greater than or equal to negative x plus 20. So my intercept is 20 on this here, and my slope is negative 1. So I'm going to end up going straight down here, 1 to 1. So it has equals, so I'm going to have a solid line. And we know it's got to be greater than this line. So I'm going to go ahead and shade everything greater than this line. Now, I'm going to go ahead and look at this equation right here. That right now I have x is greater than or equal to 1/2 of y. I'm just making my a's and the y's and my t's and the x's so that it's easy for you to read. I'm going to write this down in a way that your mind is more used to seeing it. And that would be multiply both sides by 2, so I get 2x equals, so I'm going to get y is less than or equal to 2x if I put this in something you're more familiar with. So here, like this is the same as plus 0. We have an intercept of 0, and then what I'm doing here is just come up with another point. If I said that x was 10, then y would be 20. So there's my 10, 20 point. So I'm going to go ahead and make my line, and here it is less than or equal to, so it's a solid line again. Okay. And we want everything that's less than or equal to that line. So if I put my pen on this line, when I come down, I'm in this area, I need to shade everything down this way. It starts looking really messy. And my last equation then is that t plus a has to be less than or equal to 50. Well, this equation would end up being y is less than or equal to negative x plus 50. That's what I'd end up with here. So it's going to go from 50 to 50. If I put a 50 in for my x, I get 0 for my y. That's how I come up with this point. So I get 0, 50 because 50 is the y-intercept. And I get this other point of 50, 0, because if I put a 50 in for my x, negative 50 plus 50 is 0. So then here it is. Now, and it would be everything less than that. So it's everything down here. Everything under this line. So I guess I'm running out of shapes to color with. But what I end up with when you look at this and you break it down, and it's really messy, is that this area in here this is the area that's shaded by all of the different graphs. I made all the graphs, I shaded the areas, and this area on the graph includes everything. That, oh, I went too far. It should be like this. All right. So this is a picture of all the things that would make all of these equations work. These are all the different number of 8s. Then when we go through, we find our vertices. Hold on. I'm just taking a look at how they're proceeding through there. So what I'm going to do now is I'm going to kind of clean up this, because this is a lot of stuff on here and I want to kind of clean it up. But this is the idea that what we're really concerned with now is this feasible set that's right here. And this feasible set came from graphing all these equations. Okay, now we want to start paying attention to the cost. Basically, in this situation, they go straight from, their picture is on the top of 159, which is very similar, although cleaner than my picture. They say in the next one, this inequality can be graphed on the feasible region as shown in figure 11b. So, but what they're really, you have to go back to the idea of back on page 158. 158, down toward the bottom of the paragraph. They want to find out which of it says D equals 15t plus 10a, like our equation. To find out which of the feasible ordered pairs give the minimum cost, we need to use this equation now. And what we can do is we actually pick a number. Let's say, they say here, suppose that you wish to find the proportion of the feasible region in which the cost is less than or equal to some fixed amount, say $600,000. So they're saying that they want the cost, which is 15t plus 10a, to be less than or equal to $600,000. Now we could graph that line as well. And when we graph that line, it would restrict the region even more. And that line is shown in figure 411b on the next page. They show you that they've added that line. And how they got to the line they have is they went ahead and just solved it like this. They get 10a is less than or equal to negative 15t. Then they divide through by 10. So you get a is less than or equal to negative 3/2 t plus 60. They graphed that line to get an even smaller solution set. Now you could do that with 600,000. They go on to say you could do that with 400,000. These are the different things. And I would draw it, but the page gets really messy the more I drew on this whiteboard. So what you'll find is that all of these equations, no matter what I put in for this, if I put 600, if I put 400, you're going to end up with, as you see in their graph on 160, you're going to end up with parallel lines to each other because the slope is going to be the same. It's the intercept that's going to change. And as the intercept changes, it will just slide left and right. And you can see that you could get in between certain numbers. And here they graphed two lines. They graphed a $400,000 line and a $600,000 line. And you can see that in between there would be the number of teachers or aides that you could actually do. Now they want to know, as they work down the bottom of this problem, and it just gets so messy. I apologize that I can't get more of this on here. Maybe I'll do another video working another problem. You need to look at, it says, from the graph you can tell that this is the point where the boundary lines t equal 12 and t plus a equal 20 intersect each other. What they're talking about is you're looking for the minimum number of the smallest point, the optimal point is going to be the point, it's going to be at a vertice of two of these lines that are over here. So they're saying the optimum point is right here. That's where the line t is greater than or equal to 12, this line. And t plus a greater than or equal to 20, it's where they intersect, right here. This is going to be the optimal point. And this point would be where t is 12. So if I do that, I can get 12 plus a is greater than or equal to 20. Because I'm using, if my x is 12 and t represents my x-axis, put a 12 in for my t, 12 plus a is 20, so then a must equal 8. So at the point 12, 8, I'm getting the minimum cost that I can have to support all my different things. So at 12, 8, I can go ahead and put that back in my equation. D equals 15 times 12 plus 10 times 8. And that's going to give me the magic number of $260,000 a year is the minimum cost that I can have to support all of this. Now, I realize this is messy, but I think the important thing is that you work incrementally through the problem and you rewatch the video and you work with the problem in the book. If you can understand this example, then you can understand all the other things in this book. Okay, if you want to find the biggest possible cost of this, you would, the maximum feasible cost would be the cost, the farthest to the right. That would be over here. That would be if you hire absolutely no aides and only teachers. And that would be 50 teachers and no aides, because that's the point on this graph. Where does, and here we're looking at the intersection of two other lines. The intersection of this line, t plus a is greater than or equal to 50, and also the intersection of a is greater than or equal to 0. So here's a is greater than or equal to 0. Here is t plus a is less than or equal to 50. This is the intersection. This would give us our biggest cost. If we put this back in, we would get d equals 15 times 50 plus 10 times 0. Or we'd get that, what is that, 750,000? Something like that. Yeah, $750,000. Because remember, the dollars here are in hundreds or in thousands. So the important thing that you have to learn from this is that we're trying to figure out what would give us the maximum cost or minimum cost, and those values are always going to come off of the vertices. These vertices are going to be important numbers. The ones furthest to the right will be the least, the ones furthest to the left will be the most, and sometimes that might change a little bit. Sometimes it might be tricky to know which vertice you have, so you simply figure out what the vertices are for each one of these. You plug these into this equation and it will give you the different values that you need. So also, how you find the vertice here, like this, if I wanted to find this vertice, well, it's on t is greater than or equal to 12, so that means this point, I know that my x point's already 12, because t is 12 here. And then it's also the this line here, which should be, I'm trying to figure out which one this was again. This one, yes. T is greater than or equal to 1/2 a. This one. So if I go ahead and put my 12 in for my t, I get 12 is greater than or equal to 1/2 a, 24 is greater than or equal to a, so a is 24. I need more space to do this, so I'm very constricted with this board. But the idea is that you can figure out the vertices by looking at the two lines that are intersecting and figuring out where they intersect. And when you want to do that, forget the fact that there's a greater than or equal to sign here. If I'm trying to find the intersection of this line and this line, I'm going to treat them both as if they're equal signs. And then I'm going to find their intersection. That makes life a lot easier. Forget about the greater than or equal to when you're doing the intersection. Simply use the point. Or use the equal sign. This will be a tough chapter, or a tough section. I think that the problems, they're all word problems, and so I think that we're going to do a few over different days. I'll probably do another example on a board. I might just use two boards. I might have to flip back between the two boards because obviously there's a lot of stuff to put on them. Anyway, check the internet for your homework.